Hello guys, and welcome to another tutorial for the ImpulseQt software program for gamma spectroscopy. And today I'm going to do a video on the serial device version of this software. Recently I did one for the audio device, and because the screens differ, I thought we'd do a quick video for the serial device as well. This will be another blockbuster video like the other one. So stay tuned. Today I'm going to do a test on the Atom Nano. So recently I introduced quite a few spectrometer models which work on a digital platform. So they use the FTDI chip, which is a microprocessor, and it processes the spectrum on the unit itself. So these, unlike the sound card spectrometers, these are actual MCAs. They process a spectrum on the unit and send it to the PC or Mac via USB serial connection. So it's a very different way to do a spectrum, but the software works with both styles because the connection interface is different, but the GUI for the spectrum and all the analysis, the post-recording analysis of the spectrum obviously is the same for both types of detectors. So let's see what we can do with the Atom Nano 15. This is our smallest spectrometer. It's got a cesium iodide crystal. The crystal lies lengthwise in here. It's very compact, and it's got a 15 cubic centimeter cesium iodide crystal. The connection is via USB. It's a type B socket. It plugs in to the back of the unit. A little LED comes on here, which flashes when we're actually recording a spectrum. So let me get my face out of the way here, and then I will show you what these features are. Okay, so that's good. Now, when you start ImpulseQt, it will sometimes open up in the sound card version default, or then you switch the device type up here to the serial device and restart the program, and you should be seeing this screen which you're seeing right here at the moment. If we now do a send command, the program connects to the spectrometer and retrieves the spectrometer hardware settings. All right, so we now see that we have connected to the device. We've got the temperature compensation table has come up here because these compact devices have been pre-calibrated from the factory. So there's no need for the user to change any voltages or anything like that. It's all set up ready for you to go. We have here the table showing the settings. So this is hardware version 16. It's a serial number 8125. The rise and fall of the samples, I'll show you what that is in a moment. We have a lower limit discriminator, which is set in the hardware, and some various other settings here. Now these center column here, these are the commands that are used for changing these parameters. Now once again, I like to emphasize that when you buy the monoblock spectrometers, the ones that have been pre-factory calibrated, there's generally no need to change the voltage or any of these settings. However, if you're using the GS Max 8000, which is this unit here, and you're using different style of detectors connected to the unit, then you may well need to change some of these parameters. So it's not unimportant, but if you have the monoblock version, then you really don't need to look at it. However, for those of you who do need to change settings, it's usually the voltage or the pulse shape. So we can in fact see the pulse shape here. If we click on the green button here called Pulse View, I shall show you what that does. Now this retrieves the pulse from the hardware. So what it technically does is it changes the mode of the spectrometer from spectrum mode to pulse viewing mode. And what you see here is the pulse shape plot, and you can see the little dots along this pulse shape represent the sample points that the hardware is collecting through the ADC, or the analog to digital chip. And if you want to know how the pulse shape works, you can see here that we have two commands here, rise samples and fall samples. So in this version here, we have set the rise to 6. That means 1, 2, 3, 4, 5, 6 to the peak. So there's 6 samples to the peak, and we have 11 samples in the tail, which is the fall. All right, and the correct setting is when you see the pulse beginning on the first sample and ending on the last sample. If this pulse was, for instance, floating in the air, or you're finding it below the baseline, then the settings are wrong. So those parameters would need changing. So for those of you who have a spectrometer that can be changed or should be changed, then that is done by entering the command over here in the command window. So for instance, you would enter -fall and say you wanted 12 samples instead of 11. You would simply put -fall 12 and then send that command, and that will reset the settings on the spectrometer. We can stop that again here. Now there is another mode, the oscilloscope mode, and that can be useful for setting the baseline. Okay, the baseline is the midpoint where your pulse starts and ends. So you have the baseline trim here. The command for that is -V, and that is any number from 1 to 254 or 255. So let's have a look at the oscilloscope mode. It doesn't do much here, but as you can see the pulses coming in as like an oscilloscope, and occasionally you'll see a tall pulse. If I put a source up against the detector, we'll probably see something more like this, yes. That can be useful as well. Temperature compensation can become quite complicated. There is a procedure manual where you can follow the method for temperature compensation. In the case we're demonstrating today, this Atom Nano spectrometer has been pre-calibrated from -20 to +40, I think, and it's ready to go. So the temperature compensation table is over here on the left-hand side. All right, let's go over to the histogram page and see if we can record a spectrum. And for that, we're going to need a source. So excuse me 1 second. I have a small cesium-137 check source here somewhere, yes. And we'll put that onto the spectrometer, and let's see what we can do. I'll move myself out of the way here so I'm not obstructing the actual spectrum view. So over here we enter the file name. So I can call that for CS137 test. And by default, it comes up with 8,192 channels, which is the maximum for this spectrometer. It's absolutely fine, but for demonstration purposes, it will be quicker if we just change that to 2048 bins or 2048 channels, because we'll get more counts per channel. And here we have the start and stop buttons. These are very self-explanatory. And below the start and stop buttons, we have the stop conditions. So we can set the time or the counts that we want the spectrum to stop at. So I'll set it to 1 million counts, and I'll set it, just for this demonstration, I'll set it to 60 seconds. That's big enough. And then I'll simply click start, and we shall see the spectrum starting to come in there, and you can see it's very fast. The screen updates once per second at 1 Hertz, and that's because the entire spectrum comes from the spectrometer once per second. So the screen refresh rate is the same as the spectrum is coming from the spectrometer itself. And as you can see, it's coming in very nicely. It very quickly builds up to a visible cesium-137 spectrum. And it's coming into 34 seconds, and this will automatically stop at 60 seconds. Now, the features that we have on this page here are quite easy to see, and the good thing about ImpulseQt is that I've tried as much as possible not to have any hidden settings. So there's no windows you got to pop open to find the settings or to do anything at all. It's all on the screen for you to adjust in real time. And one of the reasons I like to do it like this is because I use it every day to test detectors, and I want everything to be easily accessible. So let's go through some of the features very quickly here. This column here, we have various type of settings to change the spectrum appearance. Energy per channel, that simply takes the number of counts multiplied by the channel number. So what the effect of that is that it decreases the counts on the left-hand side and increases counts on the right-hand side, which can be very good because many detectors have low efficiency in the higher energy area, and the spectrum tends to disappear to nothing. But we can enhance that side by using the energy per bin function. The next function on here is the log scale. This you'll find on all gamma spectrum analysis softwares. And we have an option to turn calibration on, and another option to show linearity, which I'll go through in a minute. So let's quickly look at the calibration function. Okay, so in order to calibrate the spectrum, we need to first select our peaks. That's very, very simple in Impulse. You double click on the peak, and there's your region of interest. And it has found the peak and detected that the resolution of that peak is 6.2%. Okay, we can set that energy at 661.7 because we happen to know that that is cesium-137. And now we double click on the X-ray peak. And again, we can set that to 32 keV, which is the approximate value of that, and turn on calibration, and that's as simple as it is. Really, really easy to calibrate the spectrum, and that spectrum is now calibrated, and you can have more multi-point calibrations. It uses a second order polynomial to adjust the calibration. Now we have some extra features. Now we can clear those peaks again just by clicking clear peaks. And we also have a function called auto peaks, and that works together with this slider here. So if we set the bin width and click auto peaks, the system will automatically find the peaks. So in this case, it's found the X-ray peak, it's found the backscatter peak, and it's found the main cesium-137 peak. And what we can now do is we can simply pop out that table and move that around wherever you want. Quickly put in our energies here, 32 and 662. We don't have to name the backscatter peak, but if we want to put it down at about 192 or whatever it is, you can see that goes in there. And now that we have 3 peaks selected and calibrated, we may want to see if this is linear or not. And we simply turn on the linearity function. And now you can see it put some little dots up here and a line across showing the linearity. And the benefit of the linearity function is that it helps us to, it's a sanity check, or it helps us to know when we have selected the correct peaks. Had we, for instance, selected the wrong peak, you will see that the linearity, or given the wrong peak, the wrong energy, then we will see that the linearity will be completely out of whack. And that'll be a good indication that we've made a mistake. So I think that's a really handy little feature, and helps us get it right again and again. Now this table can go back up in the dock, and or you can pop that out again. And the other feature here is you can download the peaks. So once you have identified all your peaks and you're confident that you've got all the energies right, you can download the table and import that into Excel, or maybe you want to use that in a scientific paper or something like that. That'll be great. Other than that, we have the other functions on this page. We have the Gaussian correlation. That's very handy and can be helpful when we, let me clear those peaks for a second. It can be helpful to identify minor peaks. So here, for instance, we can see that the Gaussian function has found the main peaks very clearly, but it also has found indications of some peaks, smaller ones here, which aren't obvious to the naked eye. And these, so for that reason, the Gaussian correlation can be really handy. It just helps you find peaks which are not that obvious. Other functions on this page here is we have an option to pick a comparison spectrum. So let's have a look at that. We tick the comparison spectrum, and then we go here, and this long pull down, or this long drop down list here has a huge number of predefined isotope peaks that we can use as a sanity check to check what spectrum we're looking at. And it also will have your previously recorded spectra. So here again, this is what you would use if you're comparing your spectrum with a background spectrum. You would obviously record your background spectrum first, and then you would use this as a way to compare your existing spectrum to a background spectrum. And you can also subtract one from the other. So if you're using the background as a comparison, you can do a background subtraction and look at only the net counts. I won't demonstrate this here because I don't have a background spectrum taken with this particular detector. So what instead I can do is I can demonstrate it with cesium-137, which is the one we have been recording. So if I just scroll down here and find the cesium-137, you can see here that the cesium-137 peak is right on the peak here and right on the peak here. Okay, so this is the purpose of the background comparison. We can now go on and quickly hop on to the next tab here, because we've seen most of the functions here now. And this is the waterfall spectrum, and here we can click start and you'll see what happens here. So this is a spectrum over time. So this updates once per second as well, or you can set the interval. But here you can see this is the what shall I say, bird's eye view of the cesium-137 spectrum. If I was to remove the source from the detector for a moment and put it back again, you'll see there that the gap is where the source was removed. So this could be good for recording any kind of spectrum which changes over time. So this could be, for instance, analysis of soil samples, or a drilling core or something like this, where you're moving a detector along the core sample, or lowering it into a well or something like this. I think it could be most useful. It also has functions. You can show it in log scale. It makes the colors stand out a bit more. And you can download the array and so on. So, yep, pretty useful. And finally, it's the count rate chart. Now, this is purely a visible chart, and if I move myself out of the way here a bit, you can see that you can also download the count rate as well. It does not have a start and stop button here because it actually works from the main histogram page. So if I start that spectrum again and then go to the count rate, you can see here that we're now counting counts per second, which is just running off the main histogram. But it can be also useful. And when you're recording a histogram, the counts per second file records automatically together with the main spectrum. So you don't need to separately run this one here. They'll record side by side anyway, and you'll find those in the directory where you save your files, which you can actually find in the manual. And this is something I did not mention in the beginning, but on the final tab is the manual. And here you will find a comprehensive manual with every setting and every button explained to the best of my ability. Not impossible that I've forgotten one or two areas, but if I have, just email me and I will get that added into the manual for the next version. At the top of the manual, you will see the links to the folders or directories where your Impulse is saving your settings and saving your data files. So that can be quite handy if you don't know where the settings are, if you don't know where the data files end up when you save them, then you can find that on the list here. Mind you, all the download features, they will download to your downloads directory. But the actual data directory will be in your home directory. So if you're on a PC, that'll be like in the user and then / home directory. All right, so that's it for now, and thank you for watching. I think this video was a bit quicker than the last one, which is great, and hey, happy experimenting. Take care.